Okay, so 15C is about quartiles and interquartile range. So a lot of this stuff, think back to year 10 and you have seen most of it, a lot of it. So let's go through what interquartile range is again. So interquartile range considers the range of the middle 50%. That's because we don't want to be influenced too much by the outliers that could be in there. We want to see where are the majority, the middle 50%, where are those people going to be found. It is the difference between the upper and lower quartiles, and we call these Q1 for the lower quartile, which is the lower 25%, and the Q3 is the upper quartile, which means you're 3/4 of the way through the data, or 75%. Yeah, through the data. Now you're asking yourself, what is Q2 then? Why did I go from Q1 to Q3? What's Q2? The median. So you can call it Q2, or we just use the word median. So we have Q1, Q2, Q3. We subtract Q3 from Q1 to find the interquartile range, which is our middle 50% of scores. So you could be asked to make a 5-point summary, which lists the 5 pieces of information listed here. You want your lowest score and your highest score. Okay, highest and lowest. Then you have your Q1, Q2, Q3, and this 5-point summary is often used to draw box and whisker plots, or box plots we call them now. We don't tend to talk about the whiskers. Box plots, okay? Outliers, the extreme values. When you first learn about them, we just go, oh, that looks like it's separated and that might be an outlier. But then in year 10, we learned that we could actually calculate with these formulas whether something was an outlier or not. So once you've worked out what your quartiles are and your interquartile range, you do this Q1 minus 1.5 times the interquartile range, and it will give you a score. Anything below that score would be an outlier. And then this one is your upper end, Q3 plus 1.5 times the interquartile range, will tell you where you need to get to, and anything above that would be an outlier on the upper side, the high side of your data. Remember those? Yeah? Okay, so here is your box and whisker or box plot. This graph contains the 5 pieces of information. So down the bottom here it says the lowest score is 1, Q1, Q2, Q3 and highest, and they correspond with the 5 lines that are in that box plot. So lowest score 1. Q1 is 3, median is 6, Q3 is 8, and the highest score is the 9. So usually when you get your 5-point summary, you put those in as 5 vertical lines, you do a box around the middle 3, and then you do the lines or the whiskers coming out to your highest and lowest score. The only addition to that is if you do have an outlier, if something has been identified as an outlier, we mark that with a cross, and then that brings in our whiskers. But we'll be doing that in one of our questions. All right, our summary statistics, we've done these before. We can do measures of location with the mean, median, and mode. Measures of spread. So measures of location usually talk about, they're usually approximating the center of the data. So you can call them the measures of central tendency. That's these ones, mode, median, and mean. Whereas these ones, the measures of spread, how spread out are your scores? And we have things like range, interquartile range, variance, and standard deviation. All 4 of those things are talking about how spread out your data is, but in different ways. So range is the range of everything, including all of your outliers. Interquartile range is the range of your middle 50%. Your standard deviation and variance are to do with how far each of your scores are spread out from the mean. Okay? The 5-number summary, we've already talked about that, so it's there again. Skewness. Skewed to the right or positively skewed means that there is a bigger tail on the right-hand side. So that would be for a box and whisker plot. Here's your box. You'd have short on one side and a really big tail out on the right-hand side. That is called positively skewed or skewed to the right. I find that counterintuitive. I don't know about you guys, because I go, the box is leaning to the left, the data is more towards what we consider the negative values, the smaller values. But it's where the tail is how these things have been named. So the longer tail means that is positively skewed and skewed to the right. Whereas skewed to the left and negatively skewed would be going the other direction. So our box would be up here. We'd have a shorter whisker out that way and a bigger tail going out that way. And maybe like your median might be pushed up the higher end or the lower end for those as well. Does that make sense? So got to think about those, because to me, they are the opposite of what I think they should be, but that's the way they are. Okay, questions time. A die is thrown until a 6 occurs and the number n of throws is recorded. This is done 50 times and the result are recorded in the table below. So what's happening, you've got your dice and you're just seeing how many rolls does it take until you get a 6. Now, out of the 50 times that you do this experiment, you get a 6 on the first throw 4 times. That's what that means. Okay? You had to roll the dice twice, so that means on the second throw you got a 6, 5 times, and so on. So you had, in this table, there was one time when they had to roll the dice 26 times before they finally got a 6. Okay? All right, we have got the frequency and we have also got a cumulative frequency row in there. We want to find the median, the quartiles, and the interquartile range. Okay, so let's write down here, median, and then I'm going to find Q1, Q3, and the interquartile range. Okay, now, when things are in a table, it's not always as easy just to find where the middle is. You can't just look at the scores across the top. You have to consider the individual frequencies, and obviously the frequency is a lot higher towards the lower end. Okay, but we do know that we have a total of 50 times that this experiment was done. So to find the median, I want the middle of 50 scores. Yesterday when we did this, I used the n plus 1 over 2 to find the middle. Okay, so with 50 scores, I go 50 plus 1 over 2, which makes 25.5. Okay, so I'm looking through my cumulative frequency and I want to find the 25th and the 26th score because my median is in between them. So there's 22, 23, 24, 25, 26, and 27 are all in there. So that means my median is going to be at 5. Okay, then to find the quartiles, I have to halve each half of my data. So I have got, and I could draw you a little diagram like this. We started with 50 scores. I have split that to have 25 in the lower half and 25 in the upper half, right? Because my 25.5 is right in between the two 25s. Yes? Now I need to split the two 25s again. Okay, when I split those, if I do 25 plus 1 over 2, I'm going to get 26 over 2, which makes 13. I'm going to be looking for the 13th number. So I'm going to have 12 there and 12 there. I'm looking for the 13th one in the middle on that side. And on this side, 12 and 12, and there'll be the one in the middle that I'm after. The 13th one from the lower end or the 13th one from the higher end. Okay, so let's go from the lower end. 4, 9, 13 is going to be in here. Yes, so that's a median, a Q1, of 3. Going 13 back from the higher end, we had 50 scores. So 50 take away 13 is 37. So where does 37 fall? There. So it'll be in the 10. The interquartile range is the Q3 minus the Q1. So 10 take away 3, which makes 7. Obviously, all this stuff that I've done in purple, you don't need to draw, but can be helpful in working it out. Part B, draw a box and whisker. and discuss any outliers. Okay, so they've mentioned outliers. I really need to find those before I draw it. The first formula for an outlier was Q1 minus 1.5 times the interquartile range. So using the information that I just worked out, Q1 was 3, and then I minus 1.5 times the interquartile range, which was 7. Type it in your calculator. What do you get? 3 minus 1.5 times 7. Minus 7.5, is that right? Okay, good. So that would mean any score below minus 0.7 is going to be an outlier. I don't have any scores below minus 7 because it's not possible to throw something a negative number of times. Okay, so I'm not going to have any outliers on the lower end. Go to the higher end. We're going to have Q3 plus 1.5 times the interquartile range. Okay, so Q3 was 10 plus 1.5 times 7. Type that in. And this time we get 20.5. Okay, so looking at our data, do we have any scores that are above 20.5? Yes, we do. So 18 is safe, but the 22 and the 26 are both above that number. So that means, therefore, that 22 and 26 are outliers. Okay, so now we can draw our box plot. And although we love freehand, it's way better if we have a bit of a scale to use because then it's easy to read off and it's easier for you guys to mark things on there as well. So I know there's limited space, but I managed to, when I did it in my booklet, have, I had increments of, how many centimetres are different? I think each centimetre I did was 5. No, maybe not. Maybe 2 centimetres was 5. I spread it out. Anyway, let's go like this. We're going to go 0, 5, 10. Actually, I can make that bigger. I'm going to make that bigger. 25. Oh, see, really should be measuring it. The ruler on this thing is terrible for measuring, but if you guys can measure it, it'd be even better. Okay, so I've got my main 5, and then if I can get 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and I'll need an extra 1, so I need to get to 26. Okay, so let's put on our outliers. At 22, which will be here, and 26, which is there, put a cross because they're the 2 outliers that I found. So now back to part A. Actually, even before part A, I need the lowest score. The lowest score I had was 1. So I need a line at 1. Then I need my Q1, Q2, Q3. So Q1 is 3. Q2 is the median, which is 5. And Q3, which is the upper quartile, which is at 10. Normally we would have the highest score after that, but those were outliers. So what was my highest score that was not an outlier? 18. So that will be my last line up here. So we do a box joining the 3 middle lines, and then we do a little line coming out to the lowest and the highest value that was not an outlier. Okay, and we have our crosses for the 2 outliers. All right, there is our box plot. Okay, then we get into some interesting stuff. Let X be the number of tosses required to get a 6. Explain why P of 1 is equal to 1/6 and P of X equals 2 is equal to 5/6 times 1/6 and P of X equals 3 is 5/6 squared times 1/6, etc. Okay, so what is happening when we're doing the rolling of this dice, if I roll the dice once and get a 6, okay, that was a 1 in 6 chance that I would have got that 6. That's where that 1 out of 6 is coming from, right? If I had to roll the dice twice, that means that I did not roll a 6 the first time. So it means there was 5 out of 6 outcomes that I could have had the first time, because I don't want the 6. I want 1, 2, 3, 4, or 5 is fine, just not a 6. 5 out of 6 outcomes the first time, but then on the second time, I have to get a 6, all right? And then that pattern continues. So if I go x equals 3, that means I'm not getting a 6 twice. So it'd be 5 over 6 times another 5 over 6. And then on the third time, I do get my 6. So 1 out of 6 for when you finally get it. Because all of the ones in that table, all these ones here, if I'm way up here at 9, that means that I did not get a 6 8 times beforehand. Because otherwise I would have stopped earlier, right? So I missed getting a 6 8 times and finally got it on the 9th time. So what is happening is every single time it increases, I'm multiplying by an extra 5 over 6 in there. I'm not writing all that out as an explanation. We're just talking about it, okay? So you can write another one if you want to. P of x equals 4, just to show that we can continue the pattern because they gave me the first 3. 5 over 6 to the power of 3 times 1 over 6. Now, what is this actually doing when I look at these things here? It says, and use geometric progression to prove that the limiting sum of the probabilities is 1. These terms, if you like, if these are the terms of my series, every term is getting multiplied by an extra 5 over 6. So it's a GP. Okay? And if I sum up all of the terms of my series, it means I'm summing up all of the probabilities. The sum of the probabilities of an event should always be 1, and we're about to prove it with our limiting sum formula. Okay, so if the first term is equal to 1/6 and r is equal to 5 over 6 in my GP, the limiting sum formula is a over 1 minus r. So a is 1 over 6 over 1 minus 5 over 6. And guess what? It does equal 1. Pretty cool how our probability and series can all come together. All right, question D. More mixing of the probability and, not series though. Complete the following cumulative discrete probability table, giving each value correct to 3 decimal places. So, when we're using this notation, so the probability that the event which we're calling x is equal to n, and the first n is going to be n is equal to 1. So when I have to roll it once, what is the probability? Now we did it back here as fractions. The probability of getting a 1 was 1 over 6. Okay, that's just been turned into a decimal. You can type it in your calculator and you can go 1 divided by 6 and you'll get 0.16666. I think that's rounded, right? So then if we want to find the probability of x equals 2, that means we're typing this one in. We're going 5 over 6 times 1 over 6. Yeah, what's 5 over 6 times 1 over 6 to 3 decimal places? It is, yes, perfect. Okay, then to get to the next one, you're going to times that by 5 over 6 again. Because every time you're timesing it by 5 over 6, right? So this will be 0.116. Yes? Times by 5 over 6 again, 0.096. Times by 5 over 6 again, 0.080. Times by 5 over 6, 0.067. Times by 5 over 6. Obviously, I'm copying these down to save us some time. Now that would not yet equal 1, because that's not all the possible ways that you could, the number of times. In the table we had, it went up to 26. We've only gone up to 10. Okay, so that's why there is dots here, because you would need to continue that pattern for more terms if they were there. Okay, now what does this mean? Probability of capital X is less than or equal to n. So it's the probability that my outcome is less than, and I could say less than or equal to 1. This is in effect a cumulative frequency of your probability here. So if I put 5 in here, it means I would want the probabilities of everything less than or equal to 5. So I want to add all of those up to get that number there. Yeah? So the first one, that's why that one's the same. Because if it was less than or equal to 1, there is only one thing, so that one's the same. But if it's less than or equal to 2, then I'm going to go 0.167 plus the 0.139. And that will give me that box there, which makes 0.306. Okay? Then I add on the 0.116, and that gives 0.422. Add on the 0.096, and we get 0.518. Add on the next one. I'll just write them down. I hope we're all getting the idea. 0.721, 0.768, 0.807, and 0.839. So what those are saying is that for up to 10 times that you roll the dice, we're still only up to a probability, a total probability of 0.839. So there's still quite a bit of chance of having to roll more than 10 times to get our 6, right? Now that we have these as probabilities, it says find the theoretical median quartiles and interquartile ranges of that. What values of n are classified as outliers according to the interquartile range criterion? And then sketch the box plot again. Okay, so let's start with our median, and then we're going to have our Q1 and our Q3. Now this is not a cumulative frequency as in these are adding up scores. This is the total probability. If I want to find the middle of a probability, and remember that the total probabilities is always 1, where is the middle going to be? 0.5. 0.5 gives you the 50-50 chance, right? So in our data here, 0.5, that one there is just slightly above 0.5. That one there is slightly below 0.5. Okay, so the first score we're going to put in there is 4. Okay, so this one is just under. It would be during the 4, lots and lots of rolls of 4, that would be turning over in our median. So if you want an explanation to put in there, this is the first score whose cumulative probability, it's not a frequency, probability exceeds half or 0.5. So using that same logic, what do you think I'm going to do for the Q1 and the Q3? The Q1 is at the 25% line, or 0.25. So I go looking for 0.25. That's not big enough, but that's gone over. So it's going to be in here at a score of, when n equals 2. So n equals 2, because this is the first score whose cumulative probability exceeds 1/4. And Q3 will be at 0.75. So 0.721 is too small. So it's going to cross over in here at n equals 8. Now, obviously, this stuff that I'm writing afterwards, you don't need to write. Like, that's not something that you'd write on a test. But when you're looking back at your notes later, I would like you to know where those numbers came from. Okay? So we have the median, the Q1 and the Q3. I was also asked to find the interquartile range. So interquartile range, I'm just going to be subtracting the Q3 minus the Q1. So that is equal to 6. I was then asked to find, let's have a look back, find the quartiles, interquartile range. What are the values of n that are classified as outliers? Okay, so here we go with our outliers now. The formulas for outliers are Q1 minus 1.5 lots of the interquartile range. That's the first one. Q1 for our question was 2 minus 1.5 times the interquartile range, which was 6. That makes -7. Don't have any negative numbers, so there's not going to be anything on the lower end. The upper end is Q3 plus 1.5 times the interquartile range. Q3 was 8 plus 1.5 times 6, which is 17. I do have scores above 17. So anything from 18 onwards, not the 17, 17 is fine, it's anything above it. So anything 18 up is considered an outlier. All right, so let's draw ourselves a diagram. So I went up by 2s. Okay. Our lowest score in our table was a 1. The line. Our Q1 was at 2. The Q2, which is the median, was 4. The Q3 was 8. And my highest score, that is not an outlier, is going to be 17. That will be my last line. And I can do my box around those middle 3 and a little line coming out to those other 2. But everything after the 17, so the 18, 19, 20, and I'm just going to do an arrow there saying any score above those, all those scores up there are outlier. These are discrete. This is discrete probability because we can only have a whole number of throws. We can't throw a dice 3.157 times. Whole numbers, which is why I've got individual crosses at each one of those numbers and would continue going that way. One more thing to answer. Explain why both the box plot of the data and the box plot of the theoretical distribution are unsymmetrical, and how are they skewed? Okay, why aren't they symmetrical? They're not. Okay, symmetrical would mean that we've got a lovely, nice center of the data and it would be nice and evenly spread on both sides of the median. Okay? The reason that's not going to happen is because we have a 1 in 6 chance of rolling a 6. So you would expect most of the time that you would have rolled your 6 by 6 throws, right? But that is not a guarantee that that is going to happen. So we have quite a lot of other times where it's taking us a lot more than 6 times to roll that 6, which is why we have that very long tail happening on the right-hand side of our distribution. Okay? So, how are we going to explain that? Because it can sometimes take a long time to roll a 6. There is a long tail on the RHS for right-hand side. Okay, hence the data is not symmetrical. Okay, so what would we call it? Because it says comment on the skewness. So we would say it is either, no, go back and check. If we have a long tail on the right, it is skewed to the right or positively skewed. Okay, that's it. 15C.